Okay. What did we cover in the last class? Exact solutions to heat transfer problems. Until now, or transient heat transfer problem. Until now, we focused on steady state. After that, we started lumped heat transfer. But lumped heat transfer comes with the assumption that the temperature profile inside the material is not significant. The gradients are not significant. Yes? Yes? So it comes with an assumption. What if they are significant? What if you are modeling a samosa or a potato? How would you model a potato? Basically, that's the something that you learn. So this is valid for any Wyatt number. So whatever we derive today, intuitively you think, right, that whatever solution we get today should be valid for that same problem in the limit of low Wyatt number. If we solve it using lumped heat transfer, we solve it using this, they should match. You will see that. What was the problem that we were solving? Left hand side was insulated or right hand side? X equals to 0, x equals to L. And this was open to ambient, right? This is T infinity, heat transfer coefficient H. And this at T at time T is equal to 0 was it? This is the picture at T is equal to 0. This entire slab was at what temperature? Ti. Huh? And ambient temperature is T infinity and it is lower than this. So it is here. And we are interested in what happens in 1, 2, 3 TD, in the orders of few TDs, what happens. So currently the temperature profile would be here. At T is equal to 0, what should I draw? A straight line higher than T infinity. And then what should I draw here? Same heat transfer coefficient is acting on it. T infinity is T infinity throughout the problem. And then, so this is for times of order TD. That means 1 TD, 2 TD, 3 TD, something like that. And for times tending to infinity, what do you expect? Where should I draw the, what should I draw? Linear line, curved line, straight line? Straight. Where? Here, right? Because system has reached equilibrium. What should I draw here? Somewhere in between, how will it go? This was the earlier line. Should I draw from here? Should I start from here? Somewhere below? And what should I do? Just tell me what you intuitively do. This straight line? Curved line? Why curve? Why should it be curved?
Why 0?
I'm sorry?
Not from the same.
Why below? Because we have let the slab cool for some time.
It was very hot, like the temperature would not go down quickly.
So outside it was cold, inside let's say 100 degree slab. Then it could go slightly lower than 100, could go 99. These are qualitative profiles. See, eventually if it has come to this place, it has to reduce throughout. Some place it will reduce more in between, some place less. Now my question is, why did you draw it non-linear? Why did you have a curvature?
Because the del T by del T terms is non-zero in the transient phase, so there should be some curvature.
Yes. Yes, thank you. So d square T by dx square is equal to some finite number. So there has to be curvature. So this is the qualitative expectation that we have from our solution. And in order to derive the solution, what did we do? We took the transient equation. I'm not going to do it again. This is just a recap. D square T by dx square. This is a 1D problem we are solving today. We'll only focus on 1D transient because then it becomes a big issue. Is this correct? Now we had boundary conditions. T at x equal to 0 is. Let me write initial condition. T at time t equal to 0. Ti. T at x equals to 0. We can't write it. So what do we write? What should we write? Do we have a Dirichlet boundary condition or at x equals to 0? What boundary condition we have? Dirichlet. Why? That's Dirichlet. Dou t by dou x at x equal to 0 is normal boundary condition. And what is the third boundary condition? Yes. Theta beta नहीं है. At x equals to L is equal to minus h by k. T at L minus T infinity, right? And then what did we do? Before applying separation of variables or maths technique, we want to extract the dimensions out. So dimensions are hidden there in dependent and independent variables. So we gave characteristic scales. What did we do? We defined theta as t minus t infinity, ti minus t infinity, x, and then we defined x bar as x by L, right? I am a bit confused. T bar as
T by L.
T by T diffusion, right? L square by alpha. Now, what will we do? We will substitute. Instead of L, we will write x bar L. Instead of T, we will write T bar TD, and theta we will substitute by, first we will take the minus T infinity. We can do it because it's in the derivative, and then divide both the equations by T minus T infinity. Okay. After non-dimensionalizing, what did we got? D theta by dt bar is equal to del square theta by del x bar square. If you sometimes, because the board is so small, I may write small. So if you feel you can't read it, please let me know in the classroom. This is there. Now boundary conditions are theta at t bar equals to 0 is. We have already done it, so please tell me quickly. Ti minus t theta, Ti minus h1. Theta at x bar, so sorry, d theta by, dou theta, because it's partial derivatives t and x. Dou theta by dou x at x bar equals 0 is 0. And then another one, dou theta by dou x bar by x bar equals to 1 is equal to minus Biot number, because you extract the x, L out here, take L here, it becomes h, characteristic length by k. Yes? It becomes minus Biot into theta at x bar equals to 1. Now we ended up here, and then we said that since this is a homogeneous PDE, what could we write? Theta as a function of x and t bar could be written as function of x bar into function of t bar. And now what we will do, since this is homogeneous PDE, we will substitute this guess. This is called separation of variables. We are assuming that the solution is separable. And we are trying out whether there is a solution or not. Okay. So what will we do with this? to make the problem separable, we will substitute this separable solution there. It should satisfy the governing equation and boundary conditions. So what will we get? So in terms of now substituting, we will get so if this goes there, there's partial derivative with respect to t bar. So f will come out. Here g will come out. Yes, and then you will switch them so that left hand side is just one function of t and right hand side is just function of x. This is what we did last time. So now dou will become d, right? Because these are strictly this function of one variable. Dou g by dou t bar is equal to 1 by f x bar d square f by dx bar square. And what do we have for the boundary condition? Because we have to substitute there also. In time, what do we realize? Is this boundary condition homogeneous?
Yes.
This boundary condition is homogeneous.
No.
This boundary condition is homogeneous.
Yes.
This is homogeneous.
Yes.
This is homogeneous because this is a variable. It's not a constant or a function of x. So this is non-homogeneous. So we cannot separate it. We can only separate homogeneous equations. So we'll let it be. Okay. And use it later. And this will become d. Tell me, d. G to bahar aa jayega. G will come out. And then either g is, so what you will get is g of t bar df by dx at x bar equals to 0 is equal to 0. Now can this be 0? Why? Because then solution is 0. If solution is 0, your theta is 0, meaning t is equal to t infinity, meaning you are already at the equilibrium. We want out of equilibrium picture. So this cannot be 0, so this is 0. So f by dou x at x bar equals to 0, x bar equals to 0, and then dou f by dou x at x bar equals to 1 is equal to minus Biot number f at x bar equals to 1. And now what we do? Any doubts?
Yes. Can you explain how do we get to know that if a equation is homogeneous or not?
Then you have to go to your, did you do your preliminary maths course, math 101 or something? Didn't you have y double dash plus y dash is equal to 0? It's okay, we can revise again. So is this homogeneous or non-homogeneous?
Homogeneous.
This is homogeneous. This is non-homogeneous. We usually use these words to put them in category. If they are homogeneous, they can be solved using some technique. If they are not homogeneous, we have to take special action. Yes. Another example, you know complementary homogeneous solution and particular solution. When do you need to do that? When the differential equations are non-homogeneous. If they are homogeneous, you could just do homogeneous solution. Same logic. So it becomes non-homogeneous if your differential equation either ODE or PDE has a function of x or is some constant number, then it's non-homogeneous. Now you can extend that same to the boundary condition. If you have homogeneous Neumann boundary condition, meaning there will be no constant and no function of x. So this is 0. This is also homogeneous because there is no constant. It's just dependent variable just lying around. This one is non-homogeneous because it is equal to some constant. So we'll use separation of variables where we can. And now what do we do? Now I transition to today's class with the orange chalk. What is the left hand side equal to? Is this a function of x or purely a function of time? This function of time is derivative with time. So pure function of t bar. This is same way. This is pure function of x bar. So meaning this will only result in variables which are of
T.
which look like t, which smell like t, and like here x bar, but they have to be also equal. That could only be possible when
Both are constant.
both yield constant. So we use that rationale and not rub this schematic. So what we have this equal to constant, and now you have to choose. A constant can be positive, negative, 0, but only one of them is true. Can your constant, so let me write it down, 1 by g of t bar dg by dt bar equals to 1 by f x bar d square f by dx bar square is equal to some constant. So let's say I make it equals to plus lambda square. This is some number which cannot be a complex number, so I have put a square there. It's a positive quantity. You have dou g by dou t and this thing being equal to a positive number. If you were to solve this problem, what would you get? So let's take this and this. dg by dt bar is equal to plus lambda square gt. When you solve this, what will you get? Exponential to the power lambda square
into
t. This will be your gt, meaning your temperature time is flowing up to infinity.
G is a function of
G is a function of time.
so if we put time in there, we will get something in the units of second,
Yeah.
not the
Gt is a function of time, but eventually it should give you non-dimensional temperature. There will be no units. But basically, see, this function is non-dimensional. This is saying your solution is separable in something of function of space, something into function of time. Now, you can imagine fx has to be bounded because this slab is bounded. Things can blow up or decay with respect to time. This will carry that weight. This will carry that factor. And here we see this is equal to a positive number. This will blow up, which cannot be possible. There is also one more formal way you can try to find a solution and you will not find any solution. You can go ahead, assume it to be positive constant, and follow the solution approach that I'll explain to you, and you will not find any solution. Okay? So multiple ways you can rationalize that this is not possible. Can this be now 0? Can this be 0? Meaning?
either one of them has to be 0 and dt can't be 0 at denominator, so dg by dt has to be 0.
So then temperature doesn't change with time. Can that happen? No, because we're solving a transient problem. It has to change with time. So then the only possible answer is lambda square. By the way, the second case of 0, you can also go ahead and try to solve it. You will get infinitely many solutions. Okay. So even then, and this will now lead you. You will go ahead and you will find that this will lead you a unique solution. So we go ahead with this.
if it was 0, then it is steady state.
And the steady state in this problem is thermal equilibrium. You ask the question. Steady state is this. Okay. So now you have this equation. Now, I mean, it's not really an equation. This is equal to a constant. This is equal to a constant. You have to start solving one. Either you can pick these two guys, or you can pick these two guys. You can pick this equality. Which one will you choose? Would you want to solve in a homogeneous direction? You can pick GT also. You can find a solution in terms of some constant. But don't you want to solve? See, if you choose GT, you will have to close that problem with a. How many boundary conditions will it require? One. You will have to satisfy that, right? Do you have a boundary condition in G? No, right? You don't have a boundary condition. It was, we could not separate it. It was non-homogeneous. So we'll have to use what we have. So at least you can solve for F from here, right? So F, if you choose solving for F, you will get a complete solution in F. Therefore, you start with F. So what will we have? 1 by F. You can just write d square F by dx bar square equals to minus lambda square F of x bar. How would you solve this? It's nothing but y double bar is equal to minus lambda square y. How do you solve such problems? Y is equal to C1 e to the power mx plus C2 e to the power minus mx. So basically e to the power mx will substitute here and get your solution for m. What do you get? Substitute y is equal to e to the power mx, and then you get two solutions because it's a quadratic equation. What is the quadratic equation? Okay, we start with
complex.
M square is equal to. If you substitute y is equal to e to the power mx, here what equation would you get?
M square is equal to lambda square.
M square is equal to
Minus lambda square.
minus lambda square. M is equal to plus minus iota lambda. Is that true? Yeah. So you got two solutions, right? Don't worry about complexity. Sort it out. So what is fx then? Fx bar is equal to C1 e to the power minus iota lambda x bar, because m is minus iota lambda and then plus iota lambda, so it becomes minus iota lambda x bar plus C2. You can see it at the back, right? Plus C2 e to the power plus iota lambda x bar. Questions? See, I'm not using notes, so I can make mistakes. Okay. Now what should we do? Can we use something called the Euler theorem, sometimes called de Morgan theorem? Have you come across e to the power iota theta is equal to cos theta plus iota sin theta? So this could be written as f of x is equal to C1 e to the power minus iota theta, right?
Cos. Plus. Cos lambda.
This is correct.
Minus iota.
Wait, wait. Okay. So if it is minus, then what do we do? It becomes minus and minus. Where's the iota? Is this correct? And similarly, the second part, so it becomes C2 cos lambda x bar plus iota C2 sine lambda x bar lambda. Now can you take cos common and sine common and write it in terms of new constants? So what you get ultimately is f of x bar is equal to a1 cos lambda x bar plus a2 sine lambda x bar. A1 and A2 are real and complex coefficients. So A1 is real. So this will become C1 plus C2. This becomes iota C2 minus C1, some constant. We'll see that A2 becomes 0 when you use the boundary. So this is your answer for fx, but it has to be closed with two boundary conditions so that we can tell what is A1 and A2. Okay, let's do it. Okay, I'm rubbing it. You remind me what are the boundary conditions. Okay, so fx is this. What is the boundary condition we should use? Dou f by dou x at x bar equal to 0 is equal to. So let's take the derivative. Minus a1 lambda minus or plus? Plus a2 lambda cos lambda x bar. Is this correct?
Yes,
Cos x का derivative क्या होता है? That's what I've done. Now this at x bar equal to 0, so you have to put this here. So this becomes 0. This becomes 1, and this, so then this becomes 1. So what you get ultimately, and this has to be equal to 0. So then what you get?
A2
equals to 0. So any concerns you have about the, or you had about the complexity or the imaginary part, that goes to 0. You only have this remaining, and then you can use that with what? You can close that with dou f by dou x bar at x bar equals to 1 is equal to minus by f at x bar equals to 1. What left hand side is minus a1 lambda sine lambda x bar. So x bar is 1, so I just write lambda is equal to minus by f of x bar equals to 1. So this becomes not minus, plus only. A1 cos lambda. Can we get, will we get A1 from this? See, either A1 is 0, A1 can't be 0, then we get trivial solution. F becomes 0 and then everything falls down. So A1 can get cancelled. So this, surprisingly, this equation, this boundary condition is not giving you the other constant. What will it tell you? Lambda. That positive constant, that the other constant that you imagined, both things to be equal to. Right? We just said that it's some negative constant. We never said we know it. The boundary condition is now revealing it. And does it come out as clean? This is plus, this is plus. What do you get? Sin lambda by cos lambda, it becomes lambda tan lambda equals Bayet. Can you solve this? So Bayet number I will tell you whenever there is a problem, you will calculate Bayet. And if given this equation, so let's say Bayet is 5. If Bayet is 5, how will you find lambda? Is this a explicit equation where you can just find lambda? If this wasn't there, how would you find lambda? Tan inverse Bayet, but now this is there. So can you find it analytically? There will be multiple solutions, yes. But can you, what this type of equation is also called? Transcendental equation, have you heard of this? See, these are just names, okay? I'm not very big fan of these. These names, as you grow up, you'll find out that people start using these names to appear knowledgeable. But this is some equation we can't solve analytically. That's what transcendental means. How would you find it then? What are the numerical methods that you come across before? ESC 113 you have done? 112 you have done? What numerical methods? Newton-Raphson. What is it? Again, do you just know the name or do you actually know it? Any plot you have, you want to find the root, right? So basically this is a equation. I can just write this as minus Bayet equal to 0 and this is becomes fx.
You can do binary search kind of thing.
I don't know what that is. There's another name.
I can explain you the method. So basically, put some. If we'll assume some root, if the value is positive, then we'll assume
Okay.
something less. Then we can.
So trial and error.
Yeah.
But there is a better way of this, no? Newton-Raphson. Do we know the formula for it? Or did we just learn it? So we need not know the formula. So let's say if you have any curve, please pay attention here. This is now maths being revised. If you have any curve fx, and if you want to find the root, what do you do? X n plus 1 equals to xn minus f of xn by f dash of xn. But what this is actually physically what's happening, you know. You assume some number that this is the root. You draw a line. Oh, you draw a line. Draw a line, you draw a line, you draw a line, you come close to this. So what you're doing, your initial, it was xn. Then you say, okay, let me find where does it hit the curve. I'll draw a tangent. I'll draw a negative slope. So I will correct my initial guess with a new value. So I'll subtract, what will I subtract? Function of fx multiplied by the inverse of slope with a negative sign. F dash of x. N. So basically you just keep cutting the curve and keep letting the tangents meet with the x-axis. Okay, so you can do this for this. But now this is an old method. I don't want to. You guys must have done it by calculator and so on, right? Let's try an alternative way because it consumes time. I have given you a link in your resources. So when you go to the IITK, there is an hyperlink on something called Wolfram Alpha. It's like a chat-based Mathematica solver, and you can just solve it. You can just ask the question in words, and I've also typed it for you. So maybe can someone show me? So go to the end where I upload lecture things. So it's end. It says lecture companion material, na? At the end. And heat transfer below. Lecture companion material, there is Wolfram Alpha. Yeah. So click on it, and I've already typed in for you x tan x minus 5 plotted for x going from 0 to 10. That's what we want, right? We want to see how many times it cuts the x-axis, those many roots are there. Now, how many of you are there in that page? How many of you are having problem? You can't find it. So go to the lecture companion last entry and then Wolfram alpha. Those who have found it, you can make the function go not 0 to 10, you can make it 0 to 100 and see how many times it cuts the curve. Zero to 100, 0 to 1000 also you can do. How many times is it increasing? So there are infinite roots, it seems. There are infinite roots because it's a trigonometric function. So it's just like if you had sin x. How many roots does sin x have? Infinite, right? Something similar. So now you have a conundrum. This equation will yield lambda n, basically lambda 1, lambda 2, and so on. So lambda n where n belongs to integer. So you get infinite roots, that is, that f is not f, it is fn. Let's find fn, let's write fn. What will be right? So for example, can you give me some solutions for lambda, or maybe I'll give you the solution. For if beta is 5, just to give you an idea, and then you tell me if graphically it looks like that. It should be 1.314 lambda 1. Does it look like that? Lambda 2 is 4.03. Check the plot, and so on. Lambda will keep increasing. So what you have at hand?
Will we have a solution at 5.31?
5.314. This is 1.314.
Like after adding both, will we have
Adding what both? Lambdas?
lambda one?
No, lambda you don't have. Let me show you. That's what I'm doing.
Our equation is not linear. How can
F is equal to C. What was the function F? A1, na?
Cos lambda.
A1n cos lambda and x bar. Yes, please wait. Do you agree with this? Okay. What is this equation telling you? This equation is not telling you that Fn meaning n pieces in x. N tends to infinity. N is an integer. 1, 2, 3, 4, 5, 6. Number of roots that you found in your plot. Okay. And what it is saying that Fn, the solution in space, is some constant that is unknown as of now into these spatial frequencies. This is your classical Fourier representation. Any function that you see in your daily life can be decomposed into sine and cos waves. That's why you listen to music. No? It's a just mishmash of sine and cos waves. That is the idea of Fourier series. The idea here now is that if you have a spatial variation, you can decompose it into infinite frequencies. The catch is that A1n will be decaying. So you don't have to consider infinite terms. You will be okay with first few terms. Now I don't know how to now translate into real life. I didn't prepare for the real life example, but I'll come in the next class. How, if you have a linear variation or a sinusoidal variation, or sorry, square wave variation, how do you physically visualize representing in terms of sine cos waves? This is what you're having trouble with, right? Yes? But let me tell you as of now what it is not. It is not chunks in space visualized independently. It is not that.
So
Okay.
this is fnx, and for every n, different lambda and different solution would be for f of x.
Yes.
And
For different an also.
and then
If we put the summation there, we will get the final.
Summation here. We'll not put it here. We'll put it in theta.
So like
See, we don't want to put summation here. You want to get for a unique lambda, let's say lambda 1, you want to get that G1, right? Or you want to put summation before only. So we'll find G the function, and then G into F will be one unique function, and then we'll sum up all the combinations. If this is F, can you tell me what is G? How will you find G? One by G, dou G by dou T bar is equal to yes minus the one behind you who is sleeping very nicely or visualizing Fourier series. Yes sir. What is it equal to? आपके पीछे कितना चुप हो गया यार? I'm not having a sniper. Can't see you. Yes. What is it equal to? Not paying attention. Yes. One at the back. Minus lambda n square. So this is equal to so G can be found as. Tell me the solution. Take the G there. But constant. So can we call it B? Some constant. N because it hinges on what n is. E to the power minus lambda n square T bar. What is theta now? Theta is equal to. But this is for lambda n for each n. This is equal to Bn into An. Can I write it a new constant since it's only a constant? Cn cos lambda n x bar e to the power minus lambda n square t bar. Now what I mean is that you have infinite many solutions. The sum of them will also satisfy your differential equation. But you have to be careful what Cn will you use. How will you sum them together? Right? This is the argument. That theta you can write it as summation of Cn cos basically a speed. So you have decomposed the solution in infinite Fourier series type solutions, and now it all depends on how you calculate Cn, and n goes from 1 to 3 as an integer, and it's just the roots that you got here you use in solving this equation. Okay, now we have one. How would we find this?
Non-homogeneous bounding.
Yes, ma'am. How would we find this C1 or Cn? Is there any condition we haven't used yet?
yes, sir. First boundary.
First boundary condition, right? And this is a perfect time to use it. We have final solution in theta. It's a function of t bar and x bar. So let's use it. what was the equation? Theta at t bar equals to 0 is 1. And now this is equal to summation n going 1, 2, 3 and so on, Cn cos lambda n x bar e to the power minus lambda n square into time t bar. Now, what do we do?
Put T bar.
T bar equal, oh, yeah, and this becomes 1. What should we do now? What do you have? 1 is equal to C1 cos lambda 1 x bar plus C2 cos lambda 2 x bar and so on. So many, how many unknowns? How many unknowns? Infinite unknowns. How many equations? How will we find? Okay. We use a property called orthogonality of eigenfunctions. Now, this whole concept, how it comes out about, is out of your syllabus. But the principle you should remember is that the problem that you solved, in which direction was the problem homogeneous? Which direction was the problem homogeneous completely? Governing equation, boundary condition, yes. F is homogeneous because the equation is homogeneous and boundary condition is homogeneous. 0, 0 है हर जगह. Those type, that part of this problem will yield a solution. जो आपका F का solution आता है ना, क्या आता है F का? F of x bar is equal to Cn,
A1 cos
lambda and x bar. These are called eigenfunctions. These are just called some eigenfunctions. We are not interested in how they are called, why they are called eigenfunctions. We are not interested in the fact that eigen is a German word for characteristic. In other words, these are characteristic functions, meaning they define the spatial characteristic of the system. Okay, and they have a unique property called orthogonality, which translates to this. And if you did integral over the domain, if you did this eigenfunction cos lambda n x bar cos lambda m x bar dx bar, and over the domain you did this. What is the domain? X bar goes from
0 to 1.
0 to 1. If you did this, this will be 0 unless n is equal to m. So this gives you this is called Kronecker delta, basically meaning 0 if n not equal to m, and some number. So let's not introduce another jargon here. Basically, this is equal to 0 if lambda n not equal to lambda n. Non-zero if n is equal to m. Now, can we use this property? I'm not going in theory. There is a separate theory called Strum-Liouville theory, some other word for this. But can you, if you know this as an engineer, can you exploit it here? Yes. Then we'll have a few minutes break. The one, yeah, the thinking phase. Yeah. Can you exploit it here? Just think about it.
Just multiply cos lambda x term and then
integrate the entire equation
with respect to it.
So integrate the entire equation with respect to it. This is 1. So this is 1, 0 to 1. Integrate with respect to x or something else. You want to use this, right? Cos hai yahan pe, you want another cos.
Yeah, so we multiplied another cos.
Which 1, 2, 3, 4.
Which coefficient we want, we can multiply with 1.
So let's do with 1. What should I write?
Cos lambda.
Cos lambda 1 x dx bar is equal to C1 cos square lambda 1 x bar dx bar 0 to 1 plus what?
0.
0 plus 0 plus 0 and so on. So you got your solution for C1 at least. What do you have? 1 into cos lambda 1 x bar dx bar divided by, again integral, this is a separate integral, this is 0 to 1, 0 to 1, cos square lambda 1 x bar dx bar. Now can you tell me, similarly C2 you can find. So we have a solution for Cn. I should have brought the solution. 0 to 1. This is equal to some trigonometry. This will give you some sign, right? Minus sign, or no, plus sign. If you are all exhausted, I'll give you directly. Without much issue, you should get this. You can do the removal. This is your general Cn. You plug lambda n, you will get Cn. Any doubts? Is your solution now complete? Yes? What is the solution? Theta is equal to summation Cn cos lambda n x bar e to the power minus lambda n square t bar, n going from 1 to infinity. We can have, now this solution, we can have few minutes break, I think, and we can then return. Those who want to attend the remaining class can come back. You can go and have 5 minutes break. What we'll do in that remaining class, I'll plot this for you, and then I'll compare this with the lump system for you in the limit if Biot is small. Right? So we are solving this problem, right? You want to see the solution. So we'll see this, but then I'll change the Biot number to 0.001 so that your lumped formula that you use, and you'll see that it matches with this. So we'll do that. Okay, please, we'll come back in from next week. So if for a given Biot number, I am calculating my temperature profile. This is theta versus x, and now I'm going to vary time. Here you see some oscillations because even for 100 terms it's not possible to capture at early times. We'll see an example now in this class where you do some calculation. You'll find that the lower the time, the closer you are to just the initial condition, the more terms you will need. And in order to get a flat profile, शुरू में क्या temperature आपने the T is equal to Ti, right? In order to perfectly replicate that, you need infinite terms. But as soon as if you're interested in, let's say, beyond 1 microsecond or 1 millisecond, if you're interested in the remaining aspect, then you can do with 10 to 5 terms, and even beyond that, just 1 term you can do with. This is also called as first term approximation, or 1 term approximation. We'll see all that. So now you have a profile. Ignore these oscillations because the time is currently 0. Do you see the time here? See 0 here. So I'm now going to increase time. Very quickly you will see a descent. So you had an insulated wall here. Here you started convection, and it will start to cool down. Because it is at high temperature, it will have to go to equilibrium. It cools down, but as you all predicted, is it cooling down or the temperature profile is having curvature, right? It's not linear. And then it cools down, and then as some of you had confusion, why should the temperature be lower? Ultimately, it has to cool down. So throughout, the temperature will come down throughout the domain, and then okay, and eventually you get theta 0 meaning T is equal to okay. Now, what have I done here is I'm xt is the function in x and time, the exact solution. So whatever we have obtained is without any approximation. The only approximation then becomes in coding is how many terms you're going to take. But apart from that, it's perfect. What was the imperfect solution that we had before, which was only valid in certain regime? This was a lump heat transfer. It's only valid for Biot much less than 1. You had this solution. You all recall T minus T infinity, Ti minus T infinity is equal to e to the power minus T bar time constant. You can write it as Biot into T bar. Why? Because if you want to compare with this, you better have the same non-dimensional time. So T you will convert to T bar. So you will write T is equal to T bar into L square by alpha. Same non-dimensionalization. And when you resolve this, you will find it's nothing but Biot number. So lump heat transfer theta is e to the power minus Biot into time. And I call this theta lump. And then I just plot them together. And the dashed line, do you see a dashed line behind the green line? That is the lump heat transfer profile. And as I change my time, what do you observe? The profile. So let's go back. Okay, let's do this example again. I jumped ahead a bit. This is what we saw. This is what we saw going down, and you saw strong gradients, right? Why did you see strong gradients? Because Biot number was 10. So let's do 5. What we did in the class, we found lambda. Perfect. So even for 5 it's quite high, and you'll see there are strong temperature gradients. It's like samosa. You come here, you burn your hand. You thought it was cool. Now if I change Biot number to 0.05, what do you think will happen to this profile? So it will cool down altogether. It is good enough to track the surface temperature. So Joule temperature and the inside temperature should be close. And that's what you see. Very minimal curvature, but again the entire process has slowed down because their Biot number is small. Biot number small meaning HL by K, H is small. So the ambient is going to take away your heat slowly. But your temperature profile is going to be flat. It's going to slowly come down. I will not integrate for larger times. So let me do it. So you can see it come all the way down. Okay, we need more time. Now, what I'm doing here is for the small Biot regime, I'm comparing. So you see, if there is, you see that there is some mismatch. Now this mismatch should go away if I take Biot very small. Otherwise, I'm in trouble. Okay, I'm going to do it for longer times. 40. Even longer times, 500. The process is very slow now, but better than. So you see that comparison between the approximate approach and exact approach. Okay. Now, this one example I want you to solve and then you can do. I want you to do this exercise in your copies. So you have calculator, if not, you can just use your mobile phone. See, because if you're doing this for the first time, the infinite series solution, a question should come to your mind. Yeah, series to infinite. How come we are getting a solution in 100 terms? So which part of the individual term is less than, is diminishing? Now, see, we are, what is the rationale? 100 terms.
As we increase in, the denominator increases for Cn, so Cn will tend to.
So Cn, something's happening to Cn. Let's see for ourselves. Okay. So take Biot number, same problem we solved. Take Biot number equals to 5 and T bar equals to 0.2. Meaning your absolute time is 0.2 TD seconds. But for this purposes, you use T bar as 0.2 and find the profile at x bar equals to 1. And you have to also observe the terms, right? So term number 1, lambda 1 is 1.314 that we found before. 2 is 4.03, 3 is 6.91. Your lambda is increasing. Huh? So lambda is increasing. Fortunately, it's under the cos. What is the maximum value cos can admit? So lambda increasing is not that troubling. So let's see what happens to Cn. So tell me Cn using this formula and then tell me theta n, again as I said at x bar equals to 1, t bar equals to 0.2. If the contribution from third term is indeed much smaller than first term, let's see it for us. So you have to tell me what is Cn. This is the formula.
For Cn is 0.034.
Calculate all three. Is the message. Finish the calculation and then tell me. Don't worry about what I'm writing, just focus on your task.
All three are almost equal. 0.0342.
Cn is what?
0.0.
Cn is
0.0343, 0.0342, 0.0342.
Biot number is 5. It should not be there. 4 sin lambda and 2 lambda n plus sine 2 lambda n. We should get 1.24.
1.24 to the power 4.
By taking radian we get. The radian degree.
क्या हो गया बताओ ताकि सबको पता चले नहीं but so that you don't do mistake here.
Using lambda and degrees, if you take radians then
So if you take degrees. Degrees, no, we should not take degrees, right? Unless specified, it's always radians. So then, I said there is a mode in the calculator degrees or something.
No, we are calculating radians.
So Cn is
1.24
1.24,
minus 0.34
0.34,
0.15.
0.159. यार इतना तो डिक्रीज नहीं हुआ Cn. Decrease हुआ? Oh, this is plus right. You'll see that CNR of alternating signs. It's also one degree. Next one will be negative. Find lambda n. That's what matters. Lambda n first is contribution. Theta n this. So basically theta 1 I'm asking. Theta 1 is equal to okay, what is theta 1?
0.911.
0.22. And then second term? Second term? ये तो C n डालना है यहाँ पे cos lambda n x तो then 1 so this will be cos lambda n into e to the power lambda n squared, don't forget the minus lambda 1 squared into times minus 0.2. What is it? 0.008. Yes. And what is this? 10 raised to power?
Then we have to add C1 both.
No, we are calculating. See, we are calculating individual terms. We are not finding the full solution. Ultimately, you have to add. But I'm trying to tell you that.
so theta 2 is only for n equal to 2.1% of C1 plus C2. So because like for theta and we wrote a summation of Cn.
Yes.
So here we are calculating just for n equal to 2. We are not doing the summation.
We are not doing the sum. If I'm asking you, if the question is, tell me the temperature, then you have to sum them and tell me the final temperature. I'm just urging you to find out what are the individual contributions so that you know that not all terms contribute equally, and then you can chop off this infinite series to first or second term. Does it make sense? So if you do, what do you get for this last term?
9.1.
10 to the minus 6, so 10 to the minus 4, 9.17. So you see it's diminishing. So others, if you are not there later, it is indeed diminishing, right? Now, there's an exercise which you can do later. I don't ask you to do it. You can change T bar to 0.1. And what you find is that even this is very negligible. You do not need even the second term. So you see, if times, so general observation is the following by engineers, that in such problems of infinite series of this transient heat transfer, if your times are greater than 0.2, not dimensional times, or times are in dimensional terms 0.2 TD, 0.2 times the diffusion time if you are more, you can do away with the first term approximation or one term approximation, as your Sengel book will call it. If you do 0.1 now, you'll see that this will also become 10 to the minus 6 already. Times of this. If you do times larger, sorry.
0.1 is smaller.
Yeah. Greater than that. So what I meant. If you do it at times higher, then your contributions will reduce. But do another exercise for time is equal to 0.1, and you'll find that this will also contribute significantly. Since I made this confusing statement, let me repeat it. If your times are greater than 0.2 times TD, or your non-dimensional time is greater than 0.2, you can just take the first term approximation. If you're interested in smaller times, then you just trigger the heat transfer. Early times less than 0.2, you will need more terms. If T is 0.0001, you might need 10 terms. Okay, so now you have learned two techniques in transient heat transfer. This is the final remark. So if you come across any transient heat transfer equation or problem, the first instinct should be to find the Biot number, right? To see if it is indeed lumped, because if it is lumped, then life is easy, right? It's just e to the power minus Biot into time. No need to find the spatial temperature profile, no need to worry about the separation of variables. So use lump heat transfer. If no exact solution, if just hold on for one more minute now. Why are we talking? If T is greater than 0.2 TD, you use OT-FEA. If T is less than 0.2 TD, one option is to use more terms. Or there is another method that we learn in the next class called as similarity transformation, which is another approximate method but only works for small times. So, in other words, you have some small cube formula for large times, T greater than 0.2 TD, and another small cube formula for small times. You'll find it in the next class.